Today, I want to share a problem that I attempted when I first studied real analysis. So back then, I was like, what this problem is even talking about? Right? So what does it? So for any sequence from E, if the series is always convergent, right, given those conditions, E must be countable. But then I thought I cannot be just stuck in this one problem forever. So I just continued with the rest of the topics. And I even did some totally other irrelevant topics. Then I came back with a fresh mind, and I had this aha moment. So here is how it goes. So naturally, you would probably think of using proof by contradiction. Suppose E is uncountable, given these conditions, right? What kind of contradiction can we have, right? But since you soon realize that it's not going to be directly helpful, but it's going to be indirectly helpful, because if we consider some special case, right, here we have 0, 1 open interval. Special case is that, let's say, if E is the entire open interval, 0, 1, what's going to happen? Or if E is the entire half and 1 open interval, right? We all know that no matter if it's 0, 1 closed interval, open interval, half 1 closed interval, open interval, they are all uncountable, right? So what if E is this entire half 1 open interval, right? So in that case, I say it's probably going to be that since it says we can choose any sequence from E, infinite sequence, and the series is always going to be convergent, right? In that case, it's unlikely, right? Because you have if E doesn't even have to be the entire open interval. If E can just have infinitely many points here, I can already pick infinitely many points from E and make up a series so that each term is greater than half. We have infinitely many of them. How can they add up to be convergent, right? So that's a special case. And moreover, right, remember, a minimum condition for a series to be convergent is that an has to tend towards 0. Right, this is obvious, because partial sum k goes from 1 to n, ak, denoted as Sn. Right, of course, Sn minus 1 is k goes from 1 to n minus 1, ak. And Sn minus 1 is equal to, just here, the last term, an. Right, and this tends to S minus S is 0, which means an tends towards 0 is the minimum requirement for the series to be convergent. Right? Which means an cannot be too large as n gets very large. But for the initial finitely many terms, 1, 2, 3, all the way up to 2 billion, doesn't matter. Because you have finitely many terms. I'm talking about the infinitely many terms after a certain term. They cannot be too large. Right? Because an tends towards 0. But here, clearly, if this is the case, if E has infinitely many points in this open interval, then of course, like I said, you can choose infinitely many points from E. From here, then you make up a series. It's definitely going to tend towards positive infinity. Right? If that's the case, each an is greater than half. Right? Half. Of course, positive infinity. Right? So, like I said, this is a special case. Right? But E doesn't have to be open interval or doesn't have to look exactly like this, right? But the idea is the same, right? So since, like I said, E cannot have infinitely many points in half and one open interval. For the same reason, E cannot have infinitely many points in 1/3 and 1 open interval either, right? For the same reason. Otherwise, you would have, you can choose infinitely many many points from here and make sure that each term is greater than 1/3, right? You have infinitely many of them adding up, of course, tending toward positive infinity, right? Same reason. In fact, E cannot have infinitely many points in any open interval in the form of 1 over n and 1. Right? For any n that's greater than equal to 2, cannot be 1, I don't think so. Right? Any natural number greater than 2. Right? 1/4, 1/5, so on and so forth. Right? E cannot have infinitely many points in here, cannot have infinitely many points in here, cannot have infinitely many points in here, so on and so forth. And soon we immediately realize that if we construct a series of sets denoted as E sub n, where x belongs to E, that's the precondition. X is greater than 1 over n. Right, so what does that mean? Right. E half, E2 means the collection of the points in E in this open interval. E3 means the collection of the points in E that's in this open interval. E4 means the collection of the points in E that's within this open interval. Right? You continue, go on. Right? Then we realize that easily E should equal to exactly the union of En, n goes from 2 to infinity. Right? This is obvious. Right, first of all, the union of En obviously is contained in E. Right, by definition, because each En defined like this, right? First of all the points in here, first of all, they belong to E. And that's a precondition. So each En is contained in E. When you union them together, of course they are contained in E. Right? How do we know E is contained in union of En? Right? You choose any point in E. Does X also belong to the union of En? Of course, because E is contained in this 0, 1 open interval. Cannot equal to 0. Right? X cannot equal to 0, excluding the edge. So X must be greater than 0. Therefore, you can definitely find a big enough n so that X can be greater than 1 over n, right, for some big enough n. Right? This is definitely doable. Right? So that for this particular n, we have this correspondingly En, where X exactly satisfies this condition. Therefore, X belongs to this En. Right? Of course, therefore X belongs to the union of En. Therefore, you prove E is contained in the union of En also. Right? So they're equal to each other. And so that the conclusion is obvious. Right? We're pretty much done. Because like I said, I've just shown that each En, right, according to this sentence, right? Right, this is E2, E3, E4. In each En, you cannot have infinitely many points in E. Right? So that means in each of these open intervals, you only have finitely many points in E. Right? Forever. Right? So when you have right? So when you have finitely many points in each En from those points are in E, from E. When you union them, right, you have countably many En. Each En only has finitely many points from E. Right? Of course, the union is obviously countable, right? So E is obviously countable.